You can define specific visitor functions for each node type you want to handle explicitly. If you provide a specific visitor function for every node type you're interested in, you can avoid using generic underscore visit for those nodes. However, generic underscore visit is still useful as a fallback to ensure that all nodes are visited, especially when you don't want to define visitor functions for every possible node type. While you can define specific visitor functions for every node type, generic underscore visit simplifies the process by automatically handling traversal for nodes where no specific visitor function is defined. This way, you only need to define visitor functions for the node types you care about, and generic underscore visit takes care of the rest. Flexibility. Using both specific visitor functions and generic underscore visit together provides flexibility and reduces the amount of boilerplate code needed to handle AST traversal comprehensively. Boilerplate code refers to sections of code that are repeated in multiple places with little to no modification. This type of code is often necessary for a program to function but doesn't contribute to the core logic or functionality. It's essentially the template or setup code that you need to write over and over again. In the context of the AST module, manually visiting every child node for each type of node can be considered boilerplate because it's repetitive and doesn't contain the unique logic of your transformations. Using generic underscore visit reduces boilerplate code because it handles the traversal of child nodes generically, so you don't have to manually write code to visit each child node in every visitor method. Class boilerplate transformer, ast.nodeTransformer. Def visit underscore bin op, self, node. If is instance, node.op, ast, add. Node, op equals ast, sub. Hashtag manually visit child nodes. Node, left equals self.visit node.left. Node, right equals self.visit node.right. Return node. Def visit underscore function def, self, node. Hashtag example logic, add a print statement at the start. Print underscore node equals ast, expr, value equals ast, call. Func equals ast, name, ID equals print, ctx equals ast, load. Args equals ast, str, s equals f entering function node.name. Keywords plus. Node.bodied, insert, 0, print underscore node. Hashtag manually visit all statements in the function body. Node.body equals self.visit n, for n in node.body. Return node. Class generic visit transformer, ast.node transformer. Def visit underscore bin op, self, node. If is instance, node.op, ast, add. Node.op equals ast, sub. Hashtag use generic underscore visit to handle child nodes. Return self, generic underscore visit node. Def visit underscore function def, self, node. Hashtag example logic, add a print statement at the start. Print underscore node equals ast, expr, value equals ast, call. Func equals ast, name, ID equals print, ctx equals ast, load. Args equals ast, str, s equals f entering function node.name. Keywords. Node.bodied, insert, 0, print underscore node. Hashtag use generic underscore visit to handle child nodes. Return self, generic underscore visit node. Python's class mechanism can be likened to the pyramid's construction process. Just as the pyramid's layers are built with a precise mix of materials and techniques, Python's class system blends features from other languages. Minimize syntax. Python's class mechanism introduces classes with minimal new syntax, echoing simplicity in design akin to the foundational stability of the AST class. Inheritance. Similar to how each layer of the pyramid inherits and supports the layers above it, Python allows multiple base classes and method overrides, facilitating complex hierarchies and specialized behaviors within its class system. Dynamic nature. Python's dynamic nature, shared with its modules, extends to its classes. They can be created at runtime and modified afterward, enhancing flexibility and adaptability similar to how the _ASTC module dynamically generates and modifies AST nodes. Practical example. Applying the analogy. Consider a practical scenario where a Python developer wants to leverage Python's class system to create a custom data structure. 1. Define a class. Create a new Python class, inheriting properties from multiple base classes, similar to how the pyramid's layers inherit foundational properties. 2. Override methods. Override methods to customize behaviors specific to the new class, utilizing Python's flexibility in method overriding. 3. Runtime modifications. Modify the class dynamically at runtime, adapting it to changing requirements, paralleling Python's capability to modify classes post-creation. This process mirrors the flow of water through the fountain's channels and sprouts, where developers manipulate and direct the flow of AST nodes to achieve desired outcomes in their Python programs. Define a class. Custom class is defined, inheriting from base class 1 and base class 2. This reflects the pyramid's layers, inheriting foundational properties from the base classes. Doing research on classes and their attributes within a library or module is a common and essential practice in Python development and programming in general. This research helps you understand how to use the classes effectively and leverage their full capabilities. Understand functionality. To grasp what functionality a class provides and how it can be utilized. Effective use. To know how to correctly instantiate and use the class, including understanding its methods and attributes. Customization. To identify which methods can be overridden or extended to suit specific needs. Integration. To ensure the class integrates well with other parts of your code or other libraries. Let's say you want to understand how to use the AST.node transformer class. Official documentation. You'd start by reading the AST module documentation, which explains what node transformer is and provides examples. API reference. The documentation includes an API reference detailing all methods of node transformer, such as visit and generic_visit. Examples and tutorials. Look for tutorials or examples online. You might find blog posts or GitHub repositories demonstrating custom transformations. Source code. If needed, examine the source code of the AST module to see how node transformer is implemented. Ask the community. If you have specific questions or run into issues, ask on platforms like Stack Overflow. Back to defining a custom data structure, overriding methods, and performing runtime modifications. The method 1 from base class 1 is overridden in custom class to provide customized behavior, demonstrating Python's flexibility in method overriding. Let's break down the part of the code where we create an instance of custom class and call its methods. Creating an instance of custom class, obj equals custom class. This line creates a new instance of the custom class and assigns it to the variable obj. When you create an instance of a class, Python calls the class's _init_method, if it exists, to initialize the new object. Obj. This is a variable that holds a reference to an instance of the custom class. When you create an instance of a class, you are creating an object. In this case, obj is the object of custom class. The _init_method method is a special method in Python classes, often referred to as the initializer or constructor. It is automatically called when a new instance of the class is created. The purpose of _init__ is to initialize the instance's attributes and set up any initial state. The _init__ method takes self and name as parameters. Self is a reference to the current instance of the class. Self.name equals name initializes the instance's name attribute with the value passed to the _init__ method. Example: what happens during initialization? When you create a new instance with custom class Alice, Python calls the _init__ method with self referring to the new instance and name set to Alice. Inside the __init____ method, the line self.name equals name is executed. Breaking down self.name equals name. Self. Self refers to the instance of the class that is being created. It's like a placeholder for the object itself. Self.name. Self.name is an attribute of the instance. This attribute will store some data associated with the instance. By using self.name, you are defining an attribute named name for the instance. Name. Name is the parameter passed to the __init___ method. In this case, when you create an instance with custom class Alice, the value of name is Alice. Instance. Object. Imagine a box that represents an instance of a class. Each box can hold various items. Attribute. Inside the box, you can have smaller containers, like jars or compartments. Each container can hold specific items. Parameter and assignment. When you create a box, instance, and fill it with items, attributes, you assign specific items to specific containers. Assignment. This process places the items, parameters, into the containers, attributes, inside the box, instance. Print. Object. Method 1. #outputs. Custom class method 1. Overridden from base class 1. This line calls the method 1 method on the object instance of custom class. Custom class has overridden the method 1 from base class 1, so the method defined in custom class is executed. The overridden method 1 in custom class returns the string custom class method 1, overridden from base class 1, which is then printed. This line calls the method 2 method on the object instance of custom class. Custom class does not override method 2, so it inherits the method 2 implementation from base class 2. The method 2 in base class 2 returns the string base class 2 method 2, which is then printed. Runtime modifications. Modify the class dynamically at runtime, adapting it to changing requirements, paralleling Python's capability to modify classes post-creation. This process mirrors the flow of water through the fountains, channels, and sprouts, where developers manipulate and direct the flow of AST nodes to achieve desired outcomes in their Python programs. Let's break down the process of adding a new method to a class at runtime and using it. Def dynamic _ method, self. Return, dynamic method added at runtime. This defines a regular function named dynamic _ method that takes self as its only parameter. The self parameter will refer to the instance of the class when the method is called. The method simply returns the string, dynamic method added at runtime. Let's break this down. Container as a class. Imagine you have a container, which represents a class. Let's call this container shape container. This container can hold different tools and attributes that define the characteristics and behaviors of shapes stored in it. Regular function as a tool. Now, think of a function as a tool that you can use with shapes. In this case, the tool is named dynamic _ tool. This tool takes a shape as an input. The shape parameter represents a specific shape inside the container when the tool is used. Just like self in a class method refers to the instance of the class, shape refers to a specific shape instance inside the container. The dynamic _ tool simply returns a message saying, dynamic tool used at runtime. This is like the tool performing a simple action and then giving back a specific result. Let's use geometrical shapes and parameters to explain the concept of defining a function, adding it to a class, and using it dynamically. Imagine you are working with different geometrical shapes, like circles and rectangles, and you want to add a new calculation method to these shapes dynamically. Define the calculation function. Think of the calculation as a formula that you want to apply to the shapes. For example, you want to define a function that calculates the perimeter of a shape. Here, shape represents any geometrical shape that this calculation can be applied to. You have classes representing different shapes like circle and rectangle. These classes define the basic properties of the shapes, like radius for a circle and width/height for a rectangle. Self is the conventional name for the first parameter of a method in a class, referring to the instance of the class. The subsequent parameters in a method of a class are the additional inputs that the method can take to perform its functionality. These parameters provide the values needed for the method to operate on the instance of the class. They are defined after the self parameter in the method's definition. Self. The first parameter, self, is a reference to the instance of the class. It allows access to the attributes and methods of the instance. Subsequent parameters. These are additional parameters that the method requires to perform its task. They are specified after self and are used to pass values into the method. You do not have to define an __init___ method in every class. The __init___ method is used for initializing an instance's attributes when the instance is created, but if your class does not require any specific initialization, you can omit the __init___ method entirely. In such cases, the class will still work, but it won't have any custom initialization logic. When to use __init__. You should define an __init___ method in your class if initialization. You need to initialize instance attributes with specific values. Setup. You need to perform any setup operations when an instance is created. Default values. You want to set default values for certain attributes. Setup operations in the context of a class typically refer to any tasks that need to be performed when an instance of the class is created. These tasks can include initializing attributes, assigning initial values to instance attributes, resource allocation, allocating resources such as opening files, setting up network connections, or initializing complex data structures. Data validation, checking if the provided values for attributes are valid and raising errors if they are not. Calculations, performing initial calculations or data processing that is required for the instance to function correctly. Default values are initial values assigned to instance attributes if no specific values are provided during the creation of an instance. They ensure that the instance has a known and valid state, even if some attributes are not explicitly set by the user. In this example, the role attribute has a default value of guest. If no value is provided for role when creating an instance of user, it defaults to guest. Let's get back to the geometrical shapes and parameters analogy code. Calculate_perimeter is the dynamic function, or tool, in our analogy, that we are using. This function is initially defined outside of any class, and we will add it to our shape classes dynamically. This function is defined to take one parameter, shape, which represents the instance of the class it will be applied to. In a real-world scenario, this function would contain logic to calculate the perimeter of the shape, but for simplicity, it currently just returns a string. Add the function dynamically. Add the calculate_perimeter function to the circle and rectangle classes dynamically. This makes the function a method of these classes. Now, when we define a class, we already define the shapes in that class. Now, we have to create an instance of these shapes so that we can pass values as arguments to the initializer, __init__. When you create an instance of a class, you're creating a specific object that has the properties and behaviors defined by the class. The numbers 5 and 6 are the arguments passed to the constructors __init___ methods of the circle and rectangle classes, respectively.